Hello students, so this will be the last part of your third unit. So we'll discuss the remaining portions of third unit. So here we will be seeing about the RFID industry standard communication technology. So here we'll be seeing about LoRaWAN, OPC UA and MQTT protocols. So other than this, we'll be seeing about connecting into existing Modbus and Profibus technology, and we'll be seeing some basics about wireless network communication. So here we'll move on to introduction to radio frequency identification. So we are going to learn about RFID. So RFID is nothing but it's a form of wireless communication. So that it uses electromagnetic or electrostatic coupling in the radio frequency portion, and it has uniquely identify an object or person. So it uses radio frequency to check, search, identify, track, and communicate with items and peoples. So this is a method that is used to track or identify an object by radio transmission over the web. So if you consider radio frequency identification, it is a technology that uses electromagnetic fields to automatically identify and track tags attached to objects. So data is digitally encoded in an RFID tag, which can be used for which can be used to read a particular data later. So this device works as a tag, or we can call it as label. So during which data is read from the tags, and that is stored in the database through the reader, and it is compared with the traditional barcodes and QR codes. So this is often read outside the road of sight, either by passive or active RFID. So these tags contain electronically stored information, so that can be read from several meters away. So you will be using RFID commonly in inventory management, asset tracking, access control, supply chain logistics, and so on. So these are some introduction about the RFID, and here you will be learning about the RFID ID, how it works. Okay, so we'll be seeing about the RFID tag and how it is attached with the other objects. So if you see this diagram, you can see a database system RFID, where you have the reader antenna and the RFID tag. So first we'll see how RFID is attached to the object. So it is attached to the object or an item, so you want to track or identify. So RFID, it consists of a microchip and an antenna. Considering the storage, it stores unique identification data. So we have passive or no internal power supply, and it gets powered by the signal sent from the reader antenna. We'll see about what happens to the reader antenna. So we'll see some basic functions about reader antenna. So it emits radio frequency signals to power up the RFID tag. So it captures the response of data, and it can send back to the tag. And considering the RFID reader, it is connected to the antenna, and this particular thing processes the signals received from the tag, and it also extracts the data, and it converts into digital form. So it acts as the communication bridge between the tag and the database system. And moving on to the database system, so here it manages, stores and process the RFID tag data. So it checks with the tag's unique ID. So it will be checking whether there is a match between the tag's unique ID with stored records for identification, and it can be used for inventory purposes. So when you consider the flow of operation for this particular working model of RFID, so the reader antenna sends a radio signal. So this RFID tag receives power from the signal and responds when it stores the data. For example, like ID. So the RFID reader collects this data and it passes on the data. And when you consider the database system, it verifies and uses the data for applications like inventory tracking, access control, supply chain, and other management techniques. So, in short, we can say the database system is first communicated with the RFID reader and then to the reader antenna, and then it connects with the RFID tag, and some informations like data exchange is also possible, and it sends data back to the reader and finally to the database. So this is the working of an RFID. And now we'll be seeing about the types of RFID. So first we'll see UHF RFID. So we call it as ultra high frequency RFID. So there are many kinds of RFID. Each will have a different properties. So first we'll see in this particular ultra high frequency RFID. It is used on shipping pallets and some driver's licenses. So it reads and or signals from the other information responders where it communicate at distances of several meters, and they reflect the reader signals, and the reader is able to pick up these reflections. So when you consider this RFID technology, it is the most RFID tags have neither an electric plug nor a battery. So instead, all the energy needed to operate them is supplied in the form of radio waves. So this is read by the RFID reader. So this technology is called passive RFID. So this will be able to distinguish active RFID in which there is a power source on the tag. And considering the HF RFID, we call it as high frequency RFID. So it operates with 13.56 megahertz, and it is likely to be in your passport, credit cards, books, non-contact payment systems, etc. So RF, sorry, high frequency RFID has a short range, so typically we can say some meters. We have some setbacks here compared to the ultra high frequency RFID. These are the basic things, and we have some other types. So here in passive RFID, we have it has its own power source, and it uses power from the reader. So in this device, RF tags are not attached by a power supply, and passive RF tags stores their power. So here there is no need of embedded power. So we can will be using this RFID for tracking inventory, and it has a unique identification number. And this RFID is sensitive for interference, and we can say it is useful for semi-passive RFID. So when it is emitted from active antennas, the frequency will be from 125 to 134 kilohertz as low frequency, and it can have maximum of 13.56 megahertz as a high frequency, and 856 megahertz to 960 megahertz as ultra high frequency. So these are the frequency ranges of passive RFID. And next we have active RFID. So here in this device, RF tags are attached to power supply. So that basically emits a signal, and there is an antenna which receives the data. So the communication can be done over a large distance, and this RFID also has a unique identifier or an identification number. So active RFID can also be used in other devices like sensors. When you consider about the passive tags, it is the presence of a metal. So there are other forms of RFID where we can use other frequencies. For example, like LF RFID, low frequency RFID, which can be developed before HF RFID, and it is used for tracking. So next we'll move on to working principle of RFID. If you see the working principle here, so it uses radio waves to enable automatic identification and data capture. So automatic identification and data capture is denoted as AIDC function. So it uses radio waves to perform AIDC function. So when you consider this particular technology, it automatically identify objects and it collect relevant data and it map into the digital system. So these process streamlines the processes without any manual input. So here an antenna is used for a device which converts power into radio waves and which is used for communication between reader and the sender. So if you see the working of RFID, here we have RFID reader where we have a Arduino board which is connected with GSM, LCD and buffer. So, if we see the working of RFID system, there are three components. We have a scanning antenna, a transceiver, and a transponder. So, when the scanning antenna receives a signal, it is referred to as RFID reader, or we can call it as interrogator. So there are two types of RFID readers. One we call it as fixed readers and the second type we call it as mobile readers. So these readers are very much important and it can be connected with the network device. So the RFID reader is a network connected device that can be portable or it can be permanently attached to a device. So this also works under the principle of radio waves. So it uses radio waves to transmit signals that activate the tag. Once activated, the tag sends a wave back to the antenna where it is translated into the data. So when you consider transponder in the RFID tag, it has a read range where it is based on different types of tags. We have type of readers and we have RFID frequencies which is used in the surrounding environment to form RFID tags and readers. So tags have the stronger power source and also have a longer read range. So when you consider the other RFID system, so it consists of three components. As I told you, it's a scanning antenna, a transceiver, and a transponder. So based on the types of RFID reader, for example, like fixed readers and mobile readers, it is connected with a network device or it can be attached to a device. So these are the main working of RFID. And next, moving on to types of RFID tags. So here we have passive tags, and second we have active tags, and the third we have semi-passive tags. So considering the passive RFID tags, it operates without an internal power source. So they can take energy from the RFID reader signal. So when you consider passive tags, there is no built-in power source. It can directly rely on RFID reader. So it is very less expensive and it has a longer lifespan and the range can be from a few meters. So it is very cost effective and it is durable with a longer operational lifespan and it has a very limited range. And moving on to the active RFID tags, it has their own power source, for example, battery, allowing for a longer read range, for example, up to hundreds of meters. So it is basically equipped with an internal battery, so that powers both the tag and its signal transmission. So here it is active tags are more expensive compared to passive tags, so it has a limited lifespan due to the battery, and it offer extended read ranges, often reaching hundreds of meters. So it's very costly and it has a shorter lifespan due to battery depletion. And moving on to semi-passive or battery-assisted passive RFID tags, it contains a small battery that powers the tag's internal circuitry, but it actually depends on the reader to initiate the communication. So it provides a balanced solution in terms of cost, read range, and lifespan. So these are the other types of RFID. And next we have features of RFID. So RFID tag consists of two parts, which is a microcircuit and an antenna. So RFID tag is composed of two primary components. We have a microcircuit. So that microcircuit can store and process the data. An antenna that transmits and receives radio signals. So this tag is covered by a protective material, so which acts as a shield against the outer environment effect. So this tag may be passive or active, so in which we mainly use passive RFID. So to ensure the durability and reliability, the tag is most probably it is enclosed with a protective material that it shields from the environmental factors such as moisture, dust, and physical damage. So RFID tags come in two main types. So already we have seen this, active and passive. So while active tags are include built-in power source, and whereas passive RFID can rely only on energy from the reader. So these are the most uh, commonly used types for RFID tags. Three- இன்னும் மூவே ஆகல. காசுல தான் 1.32 இருக்கு 1701 இருக்கு இந்த மூவே ஆகல. ஆஹா எனக்கு எப்பவுமே இப்படிதான் இருக்கும். So when we consider the components and features of RFID, we'll consider RFID standards. Uh, so these standards have varying features where we have ISO 14443. So we have the components here where it can specify the frequency ranges from 13.56 megahertz and the power consumption approximately 10 millivolt and data throughput is 100 kbps and it operates at working distance limited to 10 centimeters and we have a component operating at 13.56 megahertz and operating distances as high as 1 meter and data throughput with few kilobits per second. And next, moving on to the frequency bands. So RFID systems operate in different frequency bands, each with its characteristics. So first, we have a low frequency. So low frequency is denoted as LF, and we have ranges from 125 to 134 kilohertz. So it is used for short range applications up to 10 centimeter, and it is very commonly used in animal tracking and in access control and high frequency is denoted as HF and we have a frequency of 13.56 megahertz and it ranges till 1 meter and it is commonly used in smart cards, ticketing and library systems and we have ultra high frequency where it is denoted as UHF and it ranges from 860 to 960 megahertz and longer range up to 12 meters. So here we will be using this ultra high frequency in inventory management, supply chain and logistics. And we have microwave frequency where we can denote 2.45 gigahertz. So it is used for very specific application which ranges similar to UHF but with a higher data transfer rates. And moving on to the challenges of RFID, the cost is really very high, and each tag costs compared to traditional barcodes, and it is very susceptible to interference from metal, liquids and other devices, and other devices like RFID systems. And we have some privacy concerns about the unauthorized tracking and data breaches. Different frequency standards and protocols can lead to compatibility issues. So it takes longer to program RFID devices, and here in RFID system we can encrypt to an extent, and in an RFID system there are 2 to 3 layers of ordinary household foil, and it can be considered for privacy concern, where anybody can access information about anything, and active RFID can be costlier uh, compared to battery, and we have so many applications of RFID. So RFID technology, since it is versatile, it can be applied in numerous fields. It is mainly used in inventory management. So it helps in tracking in real-time inventory tracking. It can also reduce errors, increases its efficiency. And considering the asset tracking, companies can monitor their assets location and status, so it can prevent loss and optimizing utilization. So when you consider supply chain management, so it enhances the visibility and accuracy in tracking products throughout the supply chain. So it is used in access control along with the security systems. It can grant or restrict access to buildings, rooms or devices. So when you consider the retail market, it enables efficient stock management, theft prevention, and improved customer experience. So in healthcare, it is used for patient tracking, equipment management, and ensuring the authenticity of medications. So next we have some advantages of RFID. Mainly we have used RFID in automation accuracy. So it helps in real-time data management. It is used in decision making. It is also used in durability, and it can be used in secured systems. So when you consider the automation, so it reduces the manual intervention, and it also minimizes errors, and it increases operational efficiency. So moving on to the accuracy, it provides the precise tracking and the collection of data as possible here, and it gives you an accurate value of some description. So based on the durability, so RFID tags are generally more durable, and it can withstand harsh environments compared to other barcodes. And based on the real-time data, it enables real-time monitoring, and it can have decision making. And when you move on to the security, so RFID system is a system provides uh, hundreds of tags which can be read in a short time, and it is very efficient, and it can be traceability for production. And comparing to the nature of the technology, RFID can be used in many sorts of application. We can use it in real time for secured devices. Moving on to the disadvantages of RFID. RFID devices often require more time to configure, and comparatively to other identification technologies, especially in complex systems, it is very tedious. So it takes longer to program RFID devices. So considering the security vulnerabilities, With other encryption and other security concerns, RFID signals can be intercepted by unauthorized readers, so it can have some potential risk to data confidentiality. So there are two or three layers of ordinary household foil to dam the radio waves. And here we have signal blocking, which can prevent unwanted scanning or signal leakage. Where in RFID systems, we'll be considering many layers. So here we have your multiple layers of common household, where all other materials can be used to block a radio wave. And considering the privacy concerns, RFID tags can be read without any direct contact. So it can raise concerns about unauthorized access to sensitive information, and it can potentially misuse of personal data. So active RFID can be costlier compared with passive RFID. So active RFID tags, which include the built-in batteries for extended range and functionality, it's comparatively costly and have a limited lifespan due to battery depletion. So next moving on to LoRaWAN. So LoRaWAN is a communication protocol. So LoRaWAN is a MAC layer protocol where we have a low power consumption, which allows devices to operate for years on a single battery. So it supports long range communication. So typically up to 15 kilometers in rural areas, and we have several kilometers in urban environments. So the protocol ensures end-to-end security. So this LoRaWAN uses encryption called as AES 128 encryption, where it can protect against replay and man-in-the-middle attacks. The protocol ensures end-to-end security with AES 128 encryption, and it protects against replay and man-in-the-middle attacks. So LoRaWAN uses adaptive data rates, so it can balance the range and data rate, optimizing battery life and network capacity. So it has three device classes. We call it as A, B, and C to cater the different IoT use cases from minimal communication to near continuous connectivity. So these are the classes. We call it as Class A, Class B, and Class C. And next we'll go for network architecture. So LoRaWAN employs a star topology where end devices communicate directly with the gateways. So the architecture consists of four main parts. So when you consider the end devices, there are sensors or actuators that transmit and receive data. So they are categorized into three classes I told you, class A, class B, and class C, are based on power consumption and communication behavior. So when you consider class A, it is considered as ultra low power usage. So we can have class A as ultra low power usage, and it has downlink communication where it occurs in response to an uplink transmission. So when you consider class A, it is ideal for battery powered devices. Moving on to class B, it has scheduled receive windows for periodic download link communication, which is suitable for applications needing regular updates. Moving on to class C, so it is continuously open receive window. So here it enables immediate downlink, but consumes more power. So here class C is mainly used for mains powered devices requiring real-time control. Moving on to the gateways, it acts as an intermediary between end devices and the network server. So it uses LoRa modulation to receive data from multiple devices simultaneously. So class A is for minimal power consumption, and class B is for scheduled downlink windows, and class C is for consuming more power, so always open to downlink. So when you consider gateways, it relay messages between end devices, and the network server using LoRa modulation. So here the gateway support bidirectional communication, and it can multicast for task like firmware updates. So, as I told you, it supports bidirectional communication and multicast. So, these particular communication is useful for tasks like firmware updates or ground commands. So, this is the basic idea of network architecture. So, here we have learned what is meant by class A, class B, and class C, and we have learned about the end devices where we can have devices like sensors or actuators that transmit and receive data, and we have some communication links, whether we can say, we can call it as downlink communication, uplink communication, multicast, and other communication which is used in these type of architecture. And next we'll move on to network architecture. So here we'll be learning about the network server. So it manages routing and deduplication and adaptive data rates. So here in the network server, it acts as a central intelligence of the LoRaWAN system. So it handles the data routing. It can also support packet deduplication and adaptive data rate management. So it is used for efficient communication between gateways and the application layer. And moving on to the application server, here it processes and visualizes data from end devices for specific use cases. So here the application server is responsible for processing, and it can analyze and visualize data received from the end devices. It can have data output which can meet use case requirements such as monitoring, alerts, or automation, etc. So these are the process or data output, we can say. And next, moving on to the advantages of LoRaWAN, we have extended coverage. So LoRaWAN usually supports long range communication, and we have long range communication, making it ideal for wide area deployments. Moving on to the energy efficiency, it can give designed for low power consumption, and it is perfect for battery operated IoT devices. And it's very cost effective infrastructure which has minimal hardware requirements and affordable deployment, where it can attract large scale applications. So high device density is also possible. A single gateway can manage thousands of end devices, enabling scalable networks for smart cities, precision architecture, and industrial monitoring. So these are the advantages here. So basically it is used in smart cities, agriculture, industrial monitoring, etc. So a single gateway can connect thousands of devices, ensuring high network capacity. So moving on to the limitations of LoRaWAN. So we have limited data rate. The protocol's low data rate extends up to 50 kilobits per second, so it is unsuitable for applications requiring high bandwidth. So LoRaWAN is not basically suitable for bandwidth in intensive tasks like video streaming or real-time data transmission. Moving on to the data latency constraints, here we can say this protocol design prioritizes power efficiency, so over speed, which may not meet the needs of time sensitive applications. So these are all the limitations of LoRaWAN. So the main thing is the limited, because of the limited data rate, there are some problems. So we have a throughput of around 50 kilobits per second, so which is not suitable for bandwidth intensive tasks like video streaming or real time data transmission. So next we'll see about the bandwidth and range of LoRaWAN. So LoRaWAN is suitable for transmitting small size payloads like sensor data over long distances. So LoRaWAN end devices are optimized to operate in low power mode, and it can last up to 10 years on a single coin cell battery. So LoRaWAN gateways can transmit and receive signals over a distance of 10 kilometers in rural areas and up to 3 kilometers in dense urban areas. So LoRa modulation provides a significantly greater communication technologies. So if you see this figure, we can see the bandwidth ranges from low to high, and the ranges from short to long. So it has varying networks where we can have deep indoor penetration. So LoRaWAN networks can provide deep indoor coverage, and it is easily cover multi-floor buildings. Based on the license, it is very expensive, and it can to afford a expensive frequency, we can go for the deployment of LoRaWAN network. So based on the geolocation, your LoRaWAN network can determine the location of end devices using triangulation without the need for GPS. Other than that, we have LoRa end device, and that can be located if at least three gateways pick up its signals. And considering the LoRaWAN network servers, which is considered to be high capacity, it handles millions of messages from thousands of gateways. So basically, when you compare with the other network, LoRaWAN has the high capacity. Public and private deployments are also possible with LoRaWAN. In public and private deployments, it is easy to deploy public and private LoRaWAN networks using the same hardware. For example, like gateways and end devices, antennas, etc., and by using software. Software, we can say UDP packet forwarders, basic stations software, LoRaWAN stacks for end devices, etc. So we can have those softwares for LoRaWAN. And moving on to the end-to-end security of LoRaWAN, it ensures secure communication between the end device and the application server. Based on the security, it uses an encryption type called as AES 128 encryption, and it has some firmware updates. So you can remotely update firmware applications to the LoRaWAN stack for a single end device or group of end devices. So LoRaWAN end devices can perform other handovers from one network to another. So its minimal infrastructure can reduce the cost of end nodes, and it can have open source of software. So when you consider about the certification, we can have a LoRa Alliance certification program. So where it certifies end devices, and it provides end users with confidence, so that the devices can be reliable and it can complement the LoRaWAN specification. Uh, so uh, LoRaWAN is a very large ecosystem. LoRaWAN is a very large ecosystem of device markers, gateways, markers, antenna markers, network service providers, and application developers. So next, moving on to open platform communications united architecture, we can represent that as OPC UA. OPC UA. And we'll see what is meant by open platform communications united architecture. So OPC UA is a data exchange standard used in industrial automation and communication, and it is independent standard with no relation to a specific system or manufacturer. And when you consider all these platform, in 1994, A group of software and hardware vendors in the industrial automation sector and other engineering disciplines formed what is now and known for the OPC Foundation. So the OPC Foundation has set out a client server, which represents a single client server specification that can allow any vendor to develop a software and applications that share the data in a fast and robust way. So at the same time, it can eliminate the other schemes that made these vendors duplicate their development efforts. So, as a result, the OPC Foundation developed in the first specification for OPC DA, Data Access Specification, was released, and in the early 1990s, the Data Access Specification was used along with the client and the server application interface, and it was constructed. Using these specification, vendors can quickly develop client software, client server software. So, open platform communications with the United Architecture, it communicates with the PC to machine communication, or it can be machine to machine communication. So next we'll be seeing about working of OPC UA. So it is available for anyone, and we can be using that particular communication, and it can implement under GPL 2.0 license. And however, since DA relies heavily on the Windows distributed component object model, many vendors has recognized the OPCDA is not truly a open standard, and it behaves poorly in a disconnected state. So it does not work well with firewalls, and it only works in Windows. To overcome the drawbacks of OPCDA, the OPC Foundation has developed OPC UA, which was significantly different from its predecessor. The goal was to move away from mainly using Windows DCOM to meet industrial automation evolving needs better. So when you consider we have cross-platform, which it was not tied to one single operating system or programming language. So, due to its increased protocol security, it provides users access to authentication, authorization, integrity, and confidentiality. The first specification of UPC UA was published in 2006, and the latest version 1.04 was released in November 2017. So it has added publish subscribe communication infrastructure, and it has also introduced new security policies. So based on the increased protocol security, it provides users access to authentication, authorization, integrity, and confidentiality. So introducing this method, it represents the function call of an object. So this object method is called, and it returns after the function is completed. So whether it is successful or not, it is invoked, and the integration of the information model is specified with and considering the integration model, it is represented as IEC 62541. So this specification is the basis of the infrastructure necessary for vendors, and it can integrate the information and model their complex data into OPC UA namespace. So, when you consider the advantages, it is rich in service-oriented architectures of OPC UA. And next, here we'll continue with the OPC UA framework. So here the field extension specified by the field level communication initiates the OPC UA framework, that is IEC 62541. So OPC UA framework supports the client server services, and it also supports protocol and publish subscribe models. and protocols. So OPC UA can run on a dedicated client and server relationship. When we consider a publish subscribe scenario, the server sends, or we can say it publishes data to the network, and the client who subscribed will receive the data. So this is all about this OPC UA, and we have some important considerations, like a specification, authentication, signing, and encryption of data, where we have heavily emphasized for both client server and publish subscribe models. So this framework provides vendors with an independent platform that allows secure and reliable information exchange. So moving on to OPC UA FLC system architecture. So this diagram explains about the open platform communication unified architecture. So this architecture provides industrial interoperability across different systems, devices, and communication layers. So when we look into this diagram, from sensors in the field to enterprise level cloud applications, we can describe in a step-by-step core concept. So here in OPC UA, which acts as a unified communication standard, so basically it connects all levels of industrial automation. And we have some field devices, as I told you before. We have some end devices like sensors or actuators, and next we have distributed control system, controllers, and DCS. And we have machines and equipment, for example like pumps, robots, etc. And we have other systems like ASCADA, MES, ERP systems, and so on. And considering the cloud and remote systems, we have satellite and mobile, and we have some layers here. So layer specifies the field level and other levels. We can have field bus, and we are going in this diagram. If we see, we have some equipments like saw, press, oil refineries, etc. So that we can consider as machines and equipment. So field devices and field bus can also be represented here. So each field devices and field bus ensures sensors and actuators collect real world process data. And Here we have advanced physical layer, where it is considered as APL. So advanced physical layer switches which connect the field devices and integrate them into the network. So OPC UA enables standardized communication from these devices upward. Okay, so it moves towards upward, and it has a controller where we can have DCS level. So this controller is represented in the middle layer. So controller for machines like saws and presses can be used, and DCS for uh, large plants like oil refineries. So altogether they aggregate, process, and they have control field data. So it ensures the interoperability between the different vendor controllers and DCS. So we have a plant enterprise system. So if you see at the top left, we have a plant enterprise system. So ERP, enterprise resource planning, and MES, manufacturing execution system, and we have SCADA, is SCADA. We can call that as supervisory control and data acquisition. So these systems use OPC UA to exchange real-time data from the plant, usually to monitor, for planning, for taking business decisions, production planning, etc. So top right, if you see, we can have some cloud and remote systems. And cloud are represented with the OPC UA securely, which transfers plant data into cloud applications. Okay, for mainly for performing analytics, AI, and optimization. And here you have a relay broker. So Relay Broker is nothing but it acts as a communication hub between the cloud and the enterprise system. So moving on to mobile robots and pump systems, we can control these pumps and robots, and it can be monitored via OPC UA. And we have satellites and satellite communication for remote monitoring and control. We'll be using satellite communication. So OPC UA allows devices and systems from different vendors to communicate perfectly. So the scalability is also increased from a single sensor to the entire enterprise system. So the flexibility is also very high. So it supports both local communication, field to controller communication, and remote or cloud connectivity is also possible here. So with these two communications, it's really very flexible. And next, moving on to security and standardization. It provides secure, standardized communication in Industry 4.0 and in IIoT environments. So these are the basic idea of system architecture of OPC UA. So it's very interoperable, it is scalable, and it is flexible. And considering the security and standardization, it really provides secure and standardized communication in Industry 4.0. So next we'll move on to OPC UA in industrial automation. So being a mission-to-mission communication protocol for industrial automation, it is a perfect candidate to connect the mission and the business networks. UPAC UA also provides data exchange, which facilitates the transfer of critical mission data. So it has some set points. It also has some measured values and process parameters across the system. So based on that, data exchange is possible. So OPC UA not only transfers mission information such as set points, measured values, and process parameters, but it can also define and describe the data. So this is done through mappings in the OPC UA specification. So considering seamless semantic data modeling, beyond simple transmission, we can use OPC UA, which also defines and structures the information through standardized mappings, and we can also ensure consistent interpretation across platforms. So basically, these industrial automation is very efficient in integration, and we can also use at higher level for business oriented software layer, and it can be used in recent applications, for example for semantic data modeling and so on, using standardized mapping techniques. So next we'll go for OPC UA in the automation pyramid. So here we can see so many layers. So the first layer is nothing but the IEEE physical layer. So next we have the network or data link layer, and next we have the use case specific protocol mappings. So built-in securities are also represented along with OPC UA. We'll be using client server model as well as publish subscribe model, where it provides services and protocols, and in publish subscribe model it provides models and protocols. And intermediate level, we have a meta model which can be represented as OPC UA meta model. And next, further on top of that, we have automation component. So on top of that, we can have motion safety instrumentation input output things, and we have companion models, and finally is the vendor specific extension. So the last two layers, we call it as IEEE models, IEEE layers, and the other layers which is represented in blue is considered to be OPC foundation plus FLC, and the last first two layers we call it as third party. So in this industrial process, we have set of points and control variables which can be easily or centrally maintained and controlled as a part of the material where we can master data. So in customer order specific information, we can directly exchange all the information. So replication of data across different software layers are also possible here. Furthermore, if you consider providing measurement and process details such as enhancement of business documents for comprehensive analytics is also an easy task in the connectivity specifying all these standards. So with Industry 4.0, the separation of the levels and the top-down approach of the information flow is considered, and it can initiate communication with other services. So we have PLC Open. So it represents the association of IEC 61131, three based controller manufacturers. So it has collaborated with OPC Foundation to define corresponding OPC UA client function blocks. So it has created a way for PLC to exchange complex data structures horizontally, and it can also include other controllers or vertically through an OPC UA servers in a manufacturing execution system. So other than manufacturing execution system, we can have ERP, that is enterprise resource planning system to receive new production orders, or we can write data to the cloud. So these all efforts are enabled in the production line to act autonomously in combination of integrated OPC UA security. So industries are used nowadays with vertical integrations using UPC UA. So each component in the industrial process, such as controller, sensor, robot, camera, and measuring device, serves as an independent mission unit, which each itself serves as OPC UA server and OPC UA client at the same time. So next we'll be seeing about MQTT protocol. So you would have already seen this protocol earlier. So message queuing telemetry transport protocol. So we represent that as MQTT. So it is a lightweight protocol where we'll be using publish subscribe messaging protocol designed mainly for mission-to-mission communication along with the Internet of Things. So when you consider the MQTT protocol, it has minimal overhead, so which is designed to operate efficiently even on devices with the constrained processing power and memory. So it has low bandwidth usage, so optimized for networks with limited data capacity. So it ensures reliable communication in remote or bandwidth sensitive environments. So it also has a scalable communication. So it is particularly useful for devices with limited resources and low bandwidth. So when you consider the features of MQTT, already I told you it's a publish subscribe model. So MQTT uses a publish subscribe model where clients communicate through a central broker. So it decouples message produces or publishes and and consumers enable scalable and flexible communication across devices. So clients can publish messages on specific topic, and other clients can subscribe to these topics to receive the messages. And this protocol is lightweight, and it is designed to be lightweight, making it suitable for resource constrained environments. So it minimizes bandwidth, and it has processing overhead. So minimal overhead, making it ideal for low bandwidth and resource constrained environments. So considering the quality of service levels, we have different levels of message delivery guarantees ranging from QoS 0 to exactly QoS 2. So this particular perfect for battery powered IoT devices. So QoS 0 represents at most once, no guarantee of delivery, and QoS 1 represents at least once, ensures message delivery may result in duplicates, and QoS 2 represents exactly once, guarantees single reliable delivery. So we have the quality of service and we have levels for that. So each level delivers a different message, and we have retained messages where we can consider brokers that can store retained messages on topics, so they can ensure the new subscribers receive most recent message immediately after the subscribing. So it also has some persistent sessions. So it maintains the session state between the client and the broker, and it allows reliable reconnections and message delivery. It also specifies last will and testament, so that is denoted as LWT. So it notifies other clients if a device disconnects unexpectedly. It enhances fault tolerance, and retained messages can also be considered, and it can store the last known good message on a topic, so new subscribers can receive the latest data immediately. So based on the security, MQTT supports various security mechanisms, including transport layer security encryption and authentication. So it supports SSL or TLS encryption. So username, password authentication, and access control for secure communication is possible here. So they have asynchronous type of communication. So devices don't need to be online simultaneously. So this particular method allows flexible and efficient message exchange. So it is platform independent, and MQTT works across various operating systems, and it is hardware platforms, making it high versatile, and it is very extensible, and it can be integrated with the other platforms. So it can also integrate along with the cloud platforms. It uses analytics engine and enterprise systems so as to communicate, and it can perform some details regarding uh, the security. So next we'll move on to architecture of MQTT. So we have some components: broker, client, and topics. So first we'll see what is meant by a broker: the central server that receives messages from clients. So it filters them based on topics, and it distributes them to the appropriate subscribers. So client device, for example, like sensor, app, gateway. So it connects to the broker. So it can be a publisher, subscriber, or both. So broker is the central server that manages all the message traffics. So it receives the message from publishers. It filters them by topic, and it forwards them to subscribers. So publisher, for example, say publisher A, client that sends message to the broker on a specific topic, and subscriber A, client that receives messages from the broker by subscribing to topics. So topic A hierarchical string can be used to label messages. So clients subscribe to topics to receive relevant data. So when you consider a client, any device or application that uses an MQTT library to connect to the broker, so client can act as a publisher, subscribers, or both. So here we have some topics. So we have represented as UTF-8. So strings are used by the broker to filter the messages for each connected clients. So it can be separated by some forward slash. So wildcards can be used to make topics more flexible. So moving on to the advantages, we have efficient data transport with minimal packet usage. So effective data dispersion and remote sensing is also possible here. And moving on to the next communication part, we have bidirectional communication, so which allows clients to publish and receive data simultaneously. So, considering the disadvantages, it can slow your send cycles compared to constrained application protocol. So, resource discovery based on flexible topic subscription is only possible here. So, lack of built-in encryption, which can rely on TLS or SSL for security. So MQTT is a versatile protocol that offers efficient and reliable communication for IoT and M2M applications, making it a popular choice for using nowadays. So next we have connecting into existing Modbus and Profibus technology. So here we have efficient communication between industrial devices and systems. So it is mainly done by optimizing operations, and it has improved with the maximum productivity. So Modbus and Profibus are the two widely used protocols in industrial automation, where we can have unique strengths of these two particular protocols. To increase the communication between industrial devices, some control system is essential for streamlining the operations, and it has also boosted productivity. So consider Modbus and Profibus. These are the widely adopted communication protocols used in industrial automation. So each offering distinct advantage tailored to specific use cases. To bridge the gap between these protocols, for example, say Modbus and Profibus conversion plays a critical role here. So it provides data exchange, and it has smoother operation, and it has enhanced its efficiency. So it enables interoperability across diverse systems, allowing efficient data exchange between devices and other devices which operate on incompatible networks. So this integration not only simplifies system architecture but also enhances operational efficiency, flexibility in complex industrial environments. So moving on to the Modbus and Profibus protocols, it is a popular communication protocol used in connecting industrial electronic devices. So basically, you have to understand the characteristics and functionalities of Modbus and Profibus protocols. So Modbus is a widely used communication protocol in industrial environments. So it is very simple, it is very flexible, and it is very yeah, easy to implement. So it enables reliable data exchange between electronic devices such as sensors, controllers, and actuators. So it makes it suitable for a broad range of automation applications. So Profibus, if you consider, we call it as process field bus, is a high-speed robust field bus protocol designed for demanding industrial automation tasks. So it also facilitates efficient communication between field devices and control systems. So it ensures precise coordination and real-time data exchange in complex manufacturing and processing environments. So next we'll move on to protocol conversion. So it involves translating data between communication protocols to enable interoperability between devices using different standards. So protocol conversion is the process of translating data between different communication standards to ensure interoperability among devices that operate using incompatible protocols. So protocol converter serves as intermediaries in this process. So it facilitates seamless communication between devices that can operate on different protocols. So when you want to understand this principle, this is essential in industrial environments where we can say we can use multiple diverse systems and equipment. So that must work together seamlessly. So we'll see some role of protocol converters. So protocol converters act as an intermediary where it can bridge the gap between devices by interpreting and reformatting data in real time. So they enable smooth communication across heterogeneous networks. So it allows the legacy systems and modern technologies to coexist, and it can elaborate effectively. So this is all about protocol conversion. And next we'll move on to efficient protocol conversion. So here we have some parameters and mechanisms for considering protocol conversion. So first we'll move on to the selecting the right protocol converter. So here choosing a protocol converter can specify some requirements based on the application, based on some factors of protocol compatibility, etc. It can also depend on communication speed and reliability. Based on the selection, the conversion of Modbus to Profibus protocols often serves several industrial applications. So when you consider interoperability of these devices, it enables communication between Modbus and Profibus devices, which gives some integration into existing industrial networks. So it also facilitates expansion of industrial systems. So it's very scalable. So enabling the integration of devices using different protocols without the need for extensive modifications. It is also really flexible, so provides flexibility in device selection and integration. So it allows manufacturers to choose the most suitable devices for the specific application requirements. So, considering the implementing error handling mechanisms, it can detect and correct communication errors. So, it can provide reliable data transmission between devices. Conducting thorough testing is possible. So, this comprehensive testing can be used to verify compatibility, reliability, and performance under different operating conditions. So along with this, efficiency is also improved. So it optimizes the data exchange between devices, and it also enhances the overall system performance and productivity. And considering the monitoring and maintenance, so regular monitor and protocol conversion system and perform preventive maintenance can be performed here. So some hardware replacements are really very costly. So preventive maintenance has to be adopted to ensure the optimal performance and reliability over time. So hardware replacements are upgrading of all the hardware component is possible, and with the use of existing devices with different communication protocols, it can also be upgraded. Next, we have wireless network communication. So next we consider So next we can consider wireless communication. So wireless communication is also referred to as unguided media or unbounded transmission media. So in this mode, we have no physical medium is required for the transmission of electromagnetic signals. So in wireless communication, we can transfer our messages through air, water, or vacuum, or like infrared, radio waves, microwaves, etc. So there are some limitations here. So infrared is used for short range communication, like TV remotes, mobile phones, personal computers, and so on. Infrared is a part of spectrum that is not visible to human eye. So the limitation of infrared rays is also specified here. So it cannot penetrate any obstacles that can use for short range. And infrared is used in night vision cameras as it has thermal properties. So we'll see some basic things with the radio waves. So it can travel large distances and it can penetrate any wall. So we can see some after seeing some limitations of infrared waves, where we can use radio waves, where we can use it in AM and FM radios, and it can be used in cordless phones. Also, with some private and government organization, it reserves certain radio frequencies for direct communication. These are very easy to generate and it can penetrate through buildings. So the requirement of radio waves is antennas, and it can send antennas where one can transmit its message and the other is receiving antenna. The frequency radio of radio wave frequency range of radio waves is 3 kilohertz to 1 gigahertz. So radio waves has some advantages like they can travel long distance in all directions and it can pass through any obstacles. And since they are considered as wireless communication mediums, there is no need for digging and spreading wires. So radio waves of frequency 300 kilohertz to 30 megahertz can travel along distances, and radio waves have some disadvantages too, like radio waves are not effective in bad weather conditions and they are less secure as they travel large distances. And next we'll see about microwaves. So microwaves are a line of side transmission. So it means both antennas which can send and receive data. So microwaves are used in mobile phones communication and it is used in television distribution. So the distance covered by the signal is directly proportional to the height of the antenna. So microwaves has a frequency range of 1 gigahertz to 300 gigahertz, and it is basically used in mobile phones communication and television distribution. So we have some advantages and disadvantages of microwaves. So when we talk about the advantages of microwaves, we can say that it is a very fast way of communication. So that can carry 25,000 voice channels at the same time. It is a wireless communication medium, so there is no need of digging and spreading of wires. There are also some limitations or demerits of microwaves. Uh, the first expense is nothing but the installation process. The maintenance are very expensive, so that really turns this into a very expensive mode of communication. So, moreover, when you consider microwaves, they are not very effective in bad weather conditions. So next we have the basics of wireless communication. Uh, so here we'll be seeing about wireless communication through radio frequency signals, which is transmitted across open space. So wireless communication takes place over free space. So with the radio frequency. So one device we call it as transmitter, and which sends the signal to another device, and the other device we call it as receiver. So this particular method which communicates with each other, we call it as wireless communication. So here we have a large number of wireless devices which communicate at the same time with the radio frequency. It can interact with each other. When you consider wireless communication, for successful communication, both devices must operate on the same frequency or channel, ensuring signal compatibility and synchronization. As the number of wireless devices operate simultaneously, it increases the likelihood of RF interference rises, and it can also disrupt signal clarity and it can reduce the communication efficiency, especially in densely populated environments. So effective frequency management and channel allocation has to be done proper. So this can be essential to minimize interference and maintain reliable wireless communication. So we'll see some basics about wireless communication. So here we'll be seeing about the unidirectional communication path. So it refers to one-way transmission of data from a sender. So sender is the transmitter to a receiver with no feedback or response from the receiving end. So it sends some data from the transmitter to the receiver. It sends the data, that's all. So it's not about the acknowledgement or any other process. So this mode is also known as simplex communication. So we have a single direction flow, and we have data travel in only one direction. There is no interaction, and the receiver cannot send back to the sender. For examples like a keyboard to computer, digital signage, data diodes, everything comes under unidirectional communication. Next, moving on to bidirectional communication. Here we have a transmitter and receiver. So it is also known as a duplex communication, where communication takes place in two-way, where exchange of data between devices or systems are possible. So in this model, both parties can send and receive information. So it can enable interactive and dynamic communication. So information travels in both directions here. So we call it as bidirectional. So considering the real-time interaction, devices can respond to each other instantly. So as soon as it receives some data, it can immediately respond to that particular data. So enhanced reliability is also possible. It supports acknowledgements, error correction, and synchronization. So here we can say some examples. It can be used in TCP/IP sockets, web sockets, industrial protocols, systems like OPC, UA, and MQTT support bidirectional messaging for control and monitoring purposes. And next we have interference with other devices. So wireless communication relies on radio frequency signals which can be transmitted through open air. So however, when multiple devices operate on overlapping or operating nearby frequencies, interference can occur. So this can disrupt the signal quality and device performance. So common causes of interference can also be considered. So for example, say co-channel interference is the problem. It can be considered here. For example, like multiple devices or networks use the same frequency channel, so it can clash, leading to a signal degradation. And for example, adjacent channel interference can also occur. So this can be possibly done like signals from nearby channels can bleed into each other, so it can cause overlapping and confusion. So non-wireless sources and environmental factors can also have some disturbances in this type of communication. So here, environmental factors we have materials like metal, concrete, and mirrors can reflect or absorb signals, weakening the communication. So magnetic noise can also can give a worse performance here. So poor electrical connections or broader RF emissions can jam or distort all the signals. So this is all about the communication devices. So till now we have seen about unidirectional communication, bidirectional communication, and interference with the other devices, and what are the possibilities of those interferences. So with this, unit 3 is over. So in the next video, we'll continue from unit 4. Thank you all. Thank you once again.